Don't you just get irritated when you walk away from a tutorial having no more understanding than you started with? Well, I hope to change that and make you into a circuit network master. What I believe to be the reason why people seem to be having trouble with circuit wiring is that the other tutorials don't tell you what is at the heart of the circuit network. I'm referring to algorithms. Wires, signals and combinators aren't hard to grasp, but a successful design depends on the plan. The arrangement of circuit network elements flows from the needs of algorithm. Learning algorithms is outside the scope of this presentation, but I will go over some practical scenarios that hopefully help to gain understanding. You can also check out Gepwin, as he has lots of different examples with explanation, or Xterminator's Building a Better Factory, link in the description. Let's start by looking at what the circuit network can do. In essence, it allows to control resource volumes. Every item in the game has an associated signal. Yes, even Steam. Then there are signals that represent abstract things and colors. The advantage of using a circuit network comes from the ability to change one signal into another, and signals that are associated to items will be perceived as actual objects by factorio elements, like liquid pumps and inserters. I'll skip the very basics and jump right into a small example. By now you will have used red cross inside a chest to limit how much it can hold, and I'm sure you know about the purple insert and how it can be configured through a filter to pick up only certain items. If you craft a red circuit wire, click it on the inserter and then click on the chest, a circuit network will be formed. Inserter will now have additional information in its context menu. As you can see, it can now evaluate two signals. If this setup were beside an assembler that produces gears, setting the first input box to gears, the evaluation operation to less than, and a constant number like 60 in the third input box, the contents of the chest would stay around 59 plus items. This happens because of the way that the evaluation is processed and inserter stack size bonus. The evaluation is read as a boolean, and inserter sees that as a flag of either continuing to work or stop. For example, if the chest has 58 gears, it evaluates it true because 58 is less than 60. If inserter has a large stack size, chest will end up with 58 plus the highest number of either available items or stack size. It is a basic example and perhaps you already knew that, but you are still having trouble bending the signals to a certain outcome. Well, another feature of circuit network is that all signals of the same type are added together. If you thought, what about the green wire? Then let's look at how they function. The wires carry two distinct categories of signals, but their values will be summed up if connected to the same circuit network. For example, if a belt and train station were connected to an electric pole, one by green, the other by red wire, and both configured to read their contents, then mousing over the electric pole would display belt items and train cargo on separate colors. This can be useful when working with the same signal from two different sources, whose values need to be kept separate. But there's always a more reliable method of changing a particular signal into a virtual one, as is the case if you wanted to compare two chests with the same contents. This wouldn't work directly because chests would need to be connected to the same decider combinator and their values would merge. This leads into a third principle, encapsulation. A lot of designs fail because they mix signals with unintended consequences. I find it easiest to think of a circuit network as a dimension that is affected by magic. Certain factorio elements can be connected to the circuit network and they behave differently. Chests, for example, send their contents as a signal, while inserters, in addition to sending the contents they are holding, can also process logic. The next time you link two or more elements, think of them as being grouped into a special dimension. Combinators can take that reality and transform it. If their output is connected back to the circuit network where input originated, the old values will be overwritten by the actions set in the combinator. Mousing over a combinator will display two sets of values, input reality and output signals. That concludes the circuit network information. Everything else is dependent on your ability to design algorithms. Let's jump into more examples. Normally you would connect progress bar like horizontally. You would add more lamps, wire them all up with the same wire, use color. You wire them all up together to read the values. See, that's how you would normally do it. You set up your lights to display contents. So for example, if I add more belts, this lamp lights up based on this evaluation. But the special case is use color. So use color is connected via the green circuit. See, this is just holds the color. And the interesting thing you can do is if I have a timer set here. So for if decider combinator takes in a signal and evaluates it and outputs it back, and its output is linked back to the input, and a constant combinator is like a chest, and every tick you can see, every tick it sends t is 1, and this combinator, because the way that signals sum up, like here it comes out, well, because it's less than 60, it sends out a signal of t, and because it loops back, it sums up with the t signal from the combinator, and now it becomes 2. And on the next tick, the network updates it and sends through, t is 2 plus this one again is 3, and so you get a clock like this. And it also sends a color, because I removed this one from here because this setup sets the color force. It will still evaluate the thing, and if the color disappears, it doesn't use the color. So very nice. You got like 1, 2, 3, 4, 5, 6 colors. I mean, technically, yeah, white. These don't display as colors, but white is the default one anyway if you don't use anything. So yeah. But the interesting thing is, let's see, the evaluation is here somewhere, less than 40. So all of these are linked, one by one, and I use a green wire here because I need to keep the red circuit network separate from the green one, because the color will conflict with this lamp. So all these horizontal lamps are connected on a green wire, but everybody else, like everybody, either vertically or horizontally, are connected by the red wire to send this value, of belts. So let's see, less than 40. What happens when it's less than 40? This evaluation fails. And so this gate sends through the color, right? And because, because of the nature of a timer and this condition, so when the timer is below 30, it doesn't send the color to the network, and we get a blinking light effect, to mark these extra special cases when, we send that color through. Otherwise, you see it on the green wire, it's linked directly to the combinator. But we take that value and we output a -1 into the network, and 1 plus 1 plus -1 becomes a 0, so the color loses. The basic idea behind it is if you have a system like this, this inserter works in a streamlined situation. you wanted to, for example, create a buffer, you know. So whenever it reaches more than 8, this inserter works. If I set it to more than 30, let's set this inserter a bit faster. See, the chest will always have a value of 30. You know, because the condition, right? And the way you get around that is by, you know, you want to empty all this 30 once 30 has acquired in the chest, not just the excess. So the way you do that is you need two elements: a decider combinator, more electricity coverage, an arithmetic combinator. And the way you do that is you link the output of the decider into the arithmetic. You link output of the arithmetic into the input of the decider, and you link input back to, well, the decider input back on itself, like decider output back to input. And what about the values? Will it conflict? Shouldn't matter. So yeah, so we need to connect the chest to the input. Let's see. The way you design it is you send a signal when it's more than 30 greens. This guy works when I have a signal. Let's stop this guy for now. So let's see. We timed this by our buffer. So in our case it's 30 minus 0 because we want it empty. So I think it would be 29 because of how math works, you know, because 0 is the first number. Let's see. So we will bump up the number of red when it is more than 30. We will output a red signal, so that will bump up our value. So this guy works when it has a red signal, I guess. I configured it. And this one will increase the electronic circuits, and once you know, it will be 59. So once the actual circuits are gone, and you know, because the phantom signal is less than this number, you know, because the chest will have 0, and our virtual signal, you know, like phantom signal will of 29 will be less than 30. You know, the system will reset, and well, you'll see it in action. So let's see, it reaches 30. You know, nothing happens, and then this guy empties it. And as you can see, input signal is now 50, but the actual chest contents is a lot less. It's easier to see if the inserter were slower. So I think now it's too slow. So you see, it works, and we could actually we could set this to freeze as well, instead of always inputting. So you see, it reaches 30, and this guy snaps, and this guy increases our signal, and that's how you get a SR latch, I think it's called. Yeah, so that's the logic. If you want to keep like 5 items in the chest, then you would set this one to 30 minus 5 and possibly minus 1. I'll try to set it to 30 and let's see if that fails this test. So 21, 24, 7. I mean, is 30 more than 30? I don't know. 29 is not more than 30, so I use, you know, minus 1. I read the contents of these chests, so with this combinator each, and I minus the values, you know, reverse the values. So these values I have in the chest, they are total values, right? I combine them with the values that I would like to have in the chests, you know, and it comes out as minus 76 barrels because 106 plus 30, you know. Then, oh, this is just a control signal to send the train away. Circuit signal 5. It reacts when something is positive. When something is positive means, you know, I don't have enough. So because we negate those numbers and they mix with the combinator, so yeah, so the train departs and loads up more. Let's see, so I have the station connected to read train contents, and for each product you have to do this separately. So I need to transform barrels into a signal, steel into a signal, and plates into a signal. And they're just, you know, straight up connected to the cargo. Then they get passed into here, and let's see, this is an AND element. So again, you have to do this operation for each separately, signal separately. But basically we take the barrels, signal C, that comes from the train, and this signal that comes from the circuit network, so minus 76. So minus 76 times the barrels in the, let's see how many barrels are there, 72. Yeah, you see C is 72. So minus value multiplied by a positive value is a negative value. As you can see, minus 4,000 something, but we're not interested in that. We're only interested, is it a plus or a minus? And the AND, if something is greater, you know, each. This one is universal, but these cannot be made universal, whatever. And this serves as an AND, you know, like if the cargo is positive and this guy is positive, that means, you know, I have a need in these chests, and the cargo has enough of that item to fulfill my need. Or rather, yeah, we don't check the values, we just check that inserters are, you know, it's okay for inserters to work, and they just, you know, evaluate it as Boolean. So either you set the filter or not. So if an item passes through, regardless of its value, if it's actually steel is positive, isn't it? Or not? It's hard. Oh yeah, it has a minus. Oh sure, sorry, yeah, has a minus in front of it. It's hard to see. So yeah, anything positive coming out of here will set the filter, you know. So it's just an algorithm, you know, it's all algorithm. Setting requests is easier because the requester chest has a built-in logic to it. But basically we have a system here. So the chests are wired together on the signal on the same circuit network and connected to this electricity pole, and their mode is set to set requests. So we have a, you know, a chest, not a chest but a combinator with the desired amounts of things we want in these chests, right? So we start from there. So we send it to a divider. You know, we send it to a central point that we would like to sum the values up with it. So let's see, this is just for the train condition, and I need to do this transformation because of this one. And same as before, you know, we read the train contents, you know, from the station, we send it through the network. What does this do? If everything less than 1, that's a different kind of logic to send the train on its way, but it takes as an input. It's hard to see. I'm not sure how I have it wired. But basically no train is here, so you know all the signals are empty. But normally what would happen, we would take what the train has as minus values. We have these values that we want to see in the train, and we use this thing, you know, these two networks, you know, like this combinator and this one, and the train values now minus meet here, and then they sum up, and then they go in as input to this combinator. So then we end up with any positive value will be used as a request. You know, anything negative, you know, you can't request minus values. And so yeah, and we need to divide it by the number of chests we have, you know, because if this chest ends up requesting 40, this one 40, this one 40, the train will be, you know, overfilled. But we divide the number that we need between the chests, and you can see it right there. We need 300, and because there's no train, you know, we don't have anything, and we divide it by, you know, for faster insertion. We could just use one chest and dump everything in there. That would take longer to insert into but basically, yeah, we divided. That's why this operation, and then we only send the request through if we have the train control signal. Now by default, you know, train can send a signal. Actually, oh, I'm using a fish. Yeah, this design was made before a train had this option. So yeah, I store a fish as a control signal, but I can't use it directly because of this transformation. It will end up as a minus value, and this one will always, you know, will never see that. This will always fail, and you know, the requesters will never be set. So you got to be very careful when you operate with these values. But since I send it on first on a green network and second directly to its input, you know, even if it mixes with the fish, you know, that is in the, well, I mean, the fish that is in the train will become negative. I send a P and train doesn't have a P, and you know, this is a virtual signal, so it will always be good on this side. And we just send any input that we receive, we send it through. So we see as input 25, 25 and 2 barrels, and that will be set in these requesters automatically. And because you know, these will disappear, these requests will disappear when the things in the train are greater, and that's why this condition, you know, when everything is in minus values, you know, so train is full, so it can depart. Let's examine what happens in the Kovarex enrichment process 40 uranium-235 and 5 uranium-238 go in, out come 41 and 2. The solution is to take one useful uranium out and leave 40 in the system for the next cycle. The algorithm with combinators is the following. One inserter takes out useful uranium and sends its hand contents in pulse mode to the network. Its stack size should be limited to 1. Arithmetic combinator takes that input and transforms it into a signal U, multiplying input by 40. The output is going back to the inserter with the condition to work when U equals 0. The signal U also goes into another inserter with condition of U more than 0. This inserter sends its hand's contents in pulse mode to another arithmetic combinator via a different color wire. Stack size should be set to largest common denominator with 40, so values like 1, 2, 5 or 10 will do. The arithmetic combinator takes in signal U from the first combinator, uranium count from the second inserter, and subtracts uranium from signal U. Output U back to input, so just loop it back. Signal U should become 0 when the cycle is done. Kovarex should now be empty and the first inserter is ready to operate. The wires coming in to first arithmetic combinator and going into the second one should be of the opposite colors to keep the uranium signals from first and second inserter separate. Let's see, the next one was... Alright, I'll show you the belt real fast. Let's imagine you have wood in your inventory. You want to insert it on a belt of your boilers or smelters or something like that. If the belt was actually full. It's hard to demonstrate it. So you read contents of this one, hold, and you enable it when everything is 0. So when this belt is empty, this one will go through, and that is a universal statement. So you don't need to worry about it. So now, what will happen is, as long as the inserter can keep up, and if it cannot keep up, if the belt is empty, you know, it will just put the products through, and you know, and this chest will take precedence over the belt, and then the belt resumes as normal. Well, it will pulsate, yeah, but you can just you know, tick it off once it's done. But yeah, as you can see, the system, that's how you inject into belts with circuit networks. You know, you just need this one condition, and then you just remember to set it off if you don't want the belt to pulsate like that. So very useful example of how to use circuit networks. Plus it also, you know, acts as a brake on a belt. You don't need to deconstruct belts or anything, you just wire them up either to a chest or to a different section of belt, you know, uncheck it, or just, you know, set a blank condition, and it will stay frozen. Very nice. And I think that more or less concludes the examples. Thanks for watching. You know, and circuit network on.